Hello, class, and welcome. If you've ever felt like you're stuck just scratching the surface with basic select statements, well, you are in exactly the right place. In this explainer, we're going way beyond the fundamentals. We're going to learn how to build some truly powerful summary reports. We'll connect data from different tables, we'll summarize it, and we'll learn to ask the kind of sophisticated questions that uncover real, meaningful insights. So, let's get right to it.
So here is our roadmap for today. First up, we're going to start by really understanding the data we're working with, especially how to handle missing information. Then we'll move on to joining it all together and summarizing it. After that, we'll get into some advanced filtering techniques. We'll even dive into nesting queries inside of other queries, and we'll wrap up with a pretty cool logic puzzle that'll let you answer almost any question you can think of. Let's kick things off with step 1.
All right, section 1. Understanding our data. Look, the first and most important rule of data analysis is this. Data is rarely perfect. It's almost never sitting there for you in one convenient file. Nope, it's scattered all over the place, across multiple tables, and even worse, it's often full of gaps.
So this is really the central challenge for any data analyst, right? How do we take all these scattered pieces and connect them to build one single coherent report? Our goal isn't just to pull data out, it's to assemble it in a way that tells a clear and, most importantly, an accurate story. And the very first piece of that story is figuring out what's missing.
Let's take a look at a sample employee table here. We've got employee IDs, names, salaries, pretty standard stuff. Now, I want you to look really closely at Ahmed's salary. Notice it's not 0 and it's not a blank space. It's null. And I absolutely cannot overstate this. Understanding this one single concept is the foundation for writing accurate, bug-free queries.
So what in the world is null? Let's try an analogy. Imagine your database is a giant filing cabinet, okay? Every employee has their own folder. Now, inside that folder, there should be a document labeled salary. For Ali, for Sarah, for Zain, that document is there. But for Ahmed, that specific piece of paper is just missing. We have no idea if his salary is 0 or $1 million. The information just isn't there. It is a true unknown, and believe me, that has huge implications for our logic.
You see, this unknown state completely changes how SQL deals with logic. In most programming, you've just got two options, true and false. But in the world of SQL, we have a third state. If you ask the database, hey, is Ahmed's salary greater than $50,000? It can't say true and it can't say false. The only honest answer it can give you is, I don't know, which in SQL is the unknown state.
And this brings us to how the database engine actually thinks. This little table here shows how our standard operators, and or and not, behave in this strange three-valued world. So let's look at the AND table. True and unknown gives you unknown, which makes sense, right? The final answer depends on that unknown value. But here's the really clever part. False and unknown always results in false. Now, why is that? Because with an AND operation, if one side is already false, the whole thing is guaranteed to be false no matter what the other side is. This logic is baked right into SQL and it affects every single query you write.
And this brings us to a classic rookie mistake. You can't write where salary equals null. Just can't do it. Why? Well, because you're basically asking the database if an unknown value is equal to another unknown value. And the answer to that is, you guessed it, unknown. To fix this, SQL gives us a special tool designed for exactly this problem. The operator is null. This is the one and only correct way to ask the database, show me the rows where this particular piece of information is missing.
Okay, section 2, joining the dots. We figured out how to handle our individual data points, even those tricky null ones. So now it's time to start assembling the full picture by connecting our separate tables using the join clause.
As you can see, SQL gives us a whole family of join operations. Now, I know this diagram might look a little intimidating at first glance, but don't worry about it. In practice, you're going to spend about 90% of your time using just two main types, the inner join and the various outer joins, especially left join. So we're going to focus on those.
But before we write our very first join, we have to talk about a critical habit, table aliases. Let's say you join an employee table and a department table. Well, all of a sudden you might have two columns named Dept ID, and the database has no idea which one you mean. That's ambiguous. So by giving employee a short alias like E and department an alias of D, our code becomes crystal clear. E.deptID equals D.deptID. It's shorter, it's unambiguous, and trust me, it is absolutely essential for writing complex queries that you and other people can actually understand later.
This slide gets to the heart of the difference. An inner join is all about finding the perfect matches. It will only give you back rows where an employee from the first table has a matching department in the second table. It's the intersection of the two sets. A left outer join, though, is totally different. It says, hey, start with the table on the left, in this case, employee, and give me every single row from it, no exceptions. Then, go and try to find a matching department. If you find one, great, put it in. If you don't find one, that's fine too. Just put null in the department columns for that row. This is your go-to tool for finding orphans in your data. You know, employees without departments or orders without customers. It's not just a join, it's a powerful data quality check. All right, section 3, summarizing the story. So we've successfully connected our tables, but what we have now is just a really long list of individual rows. That's not a report, that's just a data dump. Now we need to transform all this raw data into some meaningful insights, using what are called aggregate functions.
These 5 functions right here are the real workhorses of SQL analysis. Functions like sum, average, max, and min take an entire column of data and boil it down to one single useful number. And here's where our very first lesson comes back into play. With the exception of count star, all of these functions completely ignore null values. So when you're calculating an average salary, they don't treat Ahmed's null salary as a 0. They pretend he's not even in the calculation. Now, this is usually what you want, but you absolutely have to be aware that it's happening under the hood.
Sure, getting the average salary for the entire company is easy, right? Just AVG salary. But that's not a very useful business insight. A much better question is, what's the average salary in the research department compared to the sales department? To answer that, we're going to need a new clause.
And the solution is the group by clause. This is such a brilliant concept. When you add group by department ID, you're telling the database, okay, first, sort all of the rows into separate buckets, one for each department. Then, and only then, I want you to run the aggregate function like AVG salary on each one of those individual buckets. This is the magic that takes you from one big company-wide number to a powerful department-by-department summary report.
One last little professional tip for this section. When you calculate an aggregate, the database might name the column something kind of ugly, like AVG salary. To make your report actually readable for humans, always give it a clear, friendly name using the AS keyword. Writing AVG salary as average_salary makes your final output immediately understandable to anyone who sees it. It's a small thing, but it makes a huge difference.
Moving on to section 4, advanced filtering. So we've joined our data and we've grouped it. Now we need to filter it. But here's the twist. We now have 2 different places in our query where we can apply filters, and choosing the right one is absolutely key to getting the right answer. This slide illustrates the difference between where and having perfectly, and it all comes down to timing. The where clause is a pre-filter. It acts on individual rows before any grouping even happens. The having clause, on the other hand, is a post-filter. It acts on the entire groups after the aggregate functions have already been calculated. Think of it this way. Where filters the ingredients, having filters the finished cakes. And here we can see them working together in harmony to answer a very specific question. Let's break down the logic here, step by step. First, the where salary greater than 50,000 clause runs, and it kicks out any individual employee who makes less than that. Second, from that smaller pool of employees, the group by dept ID clause creates our department buckets. Third, the average salary gets calculated for each of those buckets. And finally, the having average salary greater than 60,000 clause looks at those final results and throws out any entire department whose average doesn't meet that final threshold. Okay, we are now entering what I think is the most powerful part of SQL. You see, sometimes to answer one question, you first have to answer another one. And this is where we learn to put queries inside of other queries. It's a technique known as nesting or using subqueries.
The concept is actually pretty simple, even though the applications are incredibly powerful. The inner query, the subquery, it runs first. It produces a result. Maybe it's a list of IDs, a single value, whatever. That result is then handed off to the outer query, which uses that information to finish its job. It's exactly like telling an assistant, okay, first go find me the list of all the projects that are managed by Smith. Then bring that list back to me and I'll use it to find every employee who works on those specific projects. It's a two-step process, but it's all automated in one single statement.
Now, one of the most common ways to use a subquery is with the in operator.
On this slide, you can see that subquery tucked away inside the parentheses. It's going to run first, and it's going to generate a list of project numbers that are associated with Smith. Then the outer query takes over and simply asks, show me all the employee information where their SSN is in that list you just generated for me. It's a very clean, very readable way to filter your main query based on a dynamic set of results from another one.
But what if you need to do more than just check if something is in a list? That's where any and all come in. They let you compare a value to the entire list that gets returned by a subquery. So for example, salary greater than any subquery is true if an employee's salary is greater than just the lowest salary in the subquery's results. But salary greater than all subquery, well, that's much stricter. It's only true if their salary is greater than the absolute highest salary that was returned by the subquery.
And finally, we have exists. This operator is a total speed demon. It doesn't care what data the subquery finds, it only cares if it finds anything at all. The subquery runs, and if it produces even one single row, exists returns true. If it returns 0 rows, it's false. So unlike in, which has to compare values one by one, exists it just checks for a pulse. It's absolutely perfect for asking questions like find all employees for whom there exists at least one entry in the dependents table. Super efficient.
For our final and most advanced lesson, we're going to tackle a concept from formal logic called universal quantification. Basically, this is all about how you ask questions that involve the word all, which is a task that's surprisingly tricky to do directly in SQL.
This seems like a pretty simple question, doesn't it? But really think about it. SQL is great at finding if a relationship exists, but it wasn't built with a direct for all command. We can't just write where employee works on all projects. It just doesn't work. So to answer this, we need to perform a very clever bit of logical gymnastics.
And here it is, the mind-bending solution. We have to completely rephrase the question. Instead of asking, find employees who work on all the projects, we ask, find employees where there does not exist a single project from that department that they do not work on. Go ahead, read that double negative again. We're looking for employees for whom the set of projects they don't work on is completely empty. It's a bit of a brain teaser, I know, but it is a perfectly logical statement that SQL can execute. This, my friends, is peak SQL wizardry.
Before we wrap up, I really want you to commit this slide to memory. This is the logical order of operations in a query, and it's different from the order you actually write it in. So even though select comes first in your code, the database actually starts with from and join to build its initial data set. Then it filters rows with where, partitions them with group by, filters those groups with having, and only at the very, very end does it execute the select to pick the columns for the final output. Understanding this execution order makes everything else, especially the difference between where and having, just click into place.
Wow. We've covered a huge amount of ground today. From understanding a single null value all the way to building complex reports with joins, aggregations, and even that mind-bending nested logic. You now have the fundamental grammar to have a deep, meaningful conversation with your data. So the only question left is, what are you going to ask?